Hello and welcome everyone to today's Applied Flow Technology webinar on Fast Impulse Fundamentals. My name is Peter Farnham and I'm a sales engineer here with Applied Flow Technology. And this is the third and final installment of our Fast Fundamentals series. Today we will be going over the top 5 fundamental AFT Impulse modeling tasks, tools, and techniques. Jumping into the agenda right here, we will be covering the basics on how to model a system with a pump trip. And in that system, we're going to be going over the basics of how to define a transient model in AFT Impulse. Then we're going to edit that model by adding a gas accumulator. After that, we're going to go into some basics on identifying cavitation in your system in AFT Impulse. Then we'll move on to sectioning your model to optimize runtime. Sectioning is a topic I'll dive into much more at a later point if you are unfamiliar with what sectioning is. And then finally, we'll wrap up by showing you guys some visualization features using color maps and animations. So we're going to get things started here by modeling a pump trip. So this model over here is what we're going to be building in Impulse. Water is going to be pumped from a lower reservoir to an upper reservoir, and during this process, the pump loses power and trips. And we are going to be modeling this in Impulse to predict the system response and showcase how the pump speed decays over time. So if y'all are brand new to the software, we have a drag and drop interface. You can see this toolbox over here at the left. If you drag these, what we call junctions, onto the workspace, just like this, and then connect them with pipes, and then double click into each one of these things to define the necessary parameters, then you have a fully defined model after defining some of the things up here, such as your fluid properties, your transient simulation time, all these things I'll go over in just a second. So some very basics on how to build a model in the software if you're completely new. In this model, I already have it defined. So we're going to be pumping up from a liquid surface elevation of 10 feet with a pipe depth of 10 feet up to an elevation of 200 feet with a pipe depth of 10 feet. Then both of these pipes right here are going to be defined as Schedule 40 ANSI steel, 4 inches in size. This lower one has a length of 10 feet. And this upper pipe right here has a length of 990 feet. And then in addition, on this pipe, we're going to be adding in some additional fittings and losses. There are a couple ways to add fittings and losses to your system. If you drop on elbows, T's, valves, anything over here at the left, it will add loss at a specific location in your system. The other way is what we're doing here is lumping in an additional K factor into your pipe by adding just an additional K of 25. So this evenly distributes this throughout the pipe if you just want a general approximation. Now getting into the transient specifics. This is where we're going to be modeling our pump trip. So in Impulse, you have to put in some sort of pump curve. Right now, we're going to be doing a standard pump curve. And we have the flow, head, and power data. You can see these two curves right here. Then in addition, in order to model a pump trip, you have to put in a rated pump speed. So we're going here with 1,760 RPM. And then in order to eliminate any sort of reverse flow through the pump, we are going to model a combined check valve right here with a forward velocity to close of 0 feet per second and then a delta head to reopen of 0 feet. So that is our standard pump defined. Now we're going to go to the transient. So there are 4 options up here, none being no transient at all, speed versus time, meaning you can define specifically what the speed of your pump is versus time and not take into account any rotating inertia. the startup and the trip over here both take into account the inertia that we would define over here, which we did right here as 25. And then down here, you have to define what is going to start this transient in your system. Right now, we're keeping it pretty simple and saying at time 0, the pump trips. So at absolute time greater than or equal to 0 seconds, start this pump trip with inertia. Now, finally, before we run this model, we have to go into our analysis setup and define a few more transient parameters. One being our fluid properties. So right now we're using water at 70 degrees. If you want to add these down here, you will double click on this or click and say add to model. Then you'll open the sectioning tab. Again, we're going to go over this a little bit later. For now, just click update and use the defaults that Impulse gives you. Those are generally a very good way to go. And then in the transient control tab, this is where you're going to define how long your transient simulation is going to run for. So from 0 to 30 seconds, we're going to be modeling this pump trip. Now, if we click run, oh, it looks like it needs to update the sectioning one more time. Here we go. Now, if we click run, you can see this model runs pretty quickly since it's relatively simple. So there are 3 ways to look at output in any of our software. One being the output tab, one being the workspace through our workspace layers feature. I'll show that a little bit later and a little bit right now as well. And then most useful for Impulse, since you are modeling a transient simulation, are the graph results over here. But briefly, I want to showcase some of the transient data in the output tab right here. So you can see at 0 seconds, our pump tripped, and at 2.259 seconds, that check valve closed because likely there was a 0 flow rate through that pump. And then this transient output right here shows you what some of the transient data is for your pipes throughout your system. And if you use this slider bar over here, you can adjust it based on the time of the simulation. On the workspace, we have this workspace layers feature. This can output things, anything from input or output data. And then, like I mentioned just a minute ago, the most useful to Impulse are graph results. So here, what we're going to be looking at are a few graphs. The first one being a pressure versus time. So you can see as the pump trips, oh, and again, we're analyzing the inlet or the suction and discharge side of the pump being the outlet of pipe 1 and the inlet of pipe 2. So you can see as this pump trips, how the pressures oscillate back and forth pretty rapidly throughout the entire simulation. Now we also want to look at a profile graph. This is displaying the maximum and minimum pressures of the entire system throughout the entire transient simulation. And one thing I want to point out for this one is you can see for about 400 feet of pipe right here, the pressure drops below atmospheric pressure. And in this case, we want to eliminate that. And that's what the gas accumulator is going to be for in the next example. We'll go over that in just a minute. So keep that in mind for the next example. And before we switch on to that next example, here is a graph of the pump speed versus time. As you can see, as that check valve closes around 2.25 seconds, the decay speed slows down pretty drastically. So going over some of the highlights that we just discussed, we learned how to build a basic transient model and define basic transients such as the pump transient trip option that we did. And then we looked at our results in a few different ways and primarily focused on the graph results. Now these junctions over here at the right, these are 11 other junctions that we allow users to define transients for in AFT Impulse. So if you want to vary pressures, vary flows, vary loss values in a valve, we allow you to do that with these 11 junctions right here. Moving on to this next example, we are going to be revising our first model by adding in a gas accumulator to try to eliminate that sub-atmospheric pressure that we were experiencing. If I switch to that scenario over here, you'll see I have this model already built. And one quick thing I'd like to touch on is how you can actually drop this gas accumulator in and split a pipe. So I drew a pipe right here. I'm just going to define this as 100 feet, for example. Now, if you hover over this gas accumulator, or any of the junctions for that matter, you can see that menu at the bottom that says to split the pipe, hold shift. So I'm going to hold shift, drag and drop onto this pipe, and then you can see it will allow me to choose how long I want each side of the pipe on either side of the gas accumulator to be. Now for this example, what we did is made pipe 4 50 feet, and then pipe 5 up here, we made that 940 feet. So it's still a total of 990 feet. We just split the pipe by adding in this gas accumulator. Now let's go look at how this is defined. So these junctions can be anywhere from pretty simple all the way up to very complex. As you start checking boxes here, more and more menus will open for you to define more and more things. Right now, we're keeping it pretty simple. We're defining a junction elevation of 10 feet, polytropic constant of 1.2, and initial gas volume of 0.5 cubic feet. And then we're going to specify this extra thing over here as a 2-foot connecting pipe to this main pipeline that has some friction and some length to it, which will affect our results ever so slightly. Now, it looks like we probably have to define the sectioning panel again. There we go. Now we can run this model and look at how the gas accumulator is affecting our results. Briefly, I want to mention this graph list manager over here. In preparation for this webinar, I pre-created these graphs and saved them over here to our graph list manager. And you do that by generating a graph using these things down here, and then clicking this plus right here to add that to the graph list. So right now we're looking at the maximum and minimum pressures of the system with the gas accumulator added. And you can see the main thing we wanted to look at is to keep the minimum pressure above atmospheric, and that gas accumulator was able to do that. Some other things that this gas accumulator was able to provide for us was less severe pressure oscillations versus time in the system. In addition, the pump speed decay is also much slower. If you remember last time, it dropped pretty rapidly and then slowed down after that check valve closed. Now it's a much more gradual decay. And then this graph is looking at the gas volume versus time of the gas accumulator. So if I go back to the workspace, we're talking about this volume right here. So the gas accumulator has both gas and liquid in it. And as the liquid fills the system and then fills back up into the gas accumulator, this gas volume increases and decreases. So that's the graph that we're looking at right here, as this oscillates back and forth to try to minimize those severe pressure waves. So in this example, we went over some basics on using the gas accumulator junction and graphing results and seeing how those changed our system by using this form of surge mitigation. If you want to learn more about gas accumulators specifically, we have a webinar that discusses this in much more detail. And it's also worth mentioning this webinar, as well as all of our previous webinars, are all posted to YouTube after the webinars finish. So if you search for applied flow technology in YouTube, you'll be able to find all 3 of these webinars that I'm mentioning down here. If you want to learn more about surge mitigation issues over here, maybe some check valve slam, because if you remember, our pump had a combined check valve, so we likely are experiencing some form of check valve slam, and specifically gas accumulators if you're interested in those. Now we're going to touch on cavitation. So we're going to move on to a new model. And this model, we are going to be defining a valve transient. So this model describes ammonia going from one pressurized tank to another pressurized tank. And in this model, we want to close the valve as fast as possible. However, if you are familiar with surge in any regard, you know that closing a valve really quickly can often lead to high pressure spikes and oftentimes cavitation as well. So we're going to go over this model and show you guys how closing this valve quickly creates pressure spikes and cavitation. And with this model, we're going to be using our scenarios to model a half a second valve closure, a 1 second valve closure, and a 2 second valve closure. And we're going to see how our results vary and how the pressure spikes are decreased as the valve closure time increases. So briefly looking at how this model was defined, we have 2 pressurized tanks that are both pressurized to 250 psig. This one has an elevation of 40 feet, and this one has an elevation of 20 feet. And then our valve transient is going to be defined as a simple user-specified valve with a fully open CV of 1,000. So these are the steady state values right here. Now we're going to define the transients. We're going to initiate this transient event based on time, similar to what we did with the pump trip. And then we're going to define that over here on the right in this table. So at time 0, we have a fully open valve. At half a second, this valve is already fully closed. And then we're going to carry out that simulation for another 5 seconds. And then looking into our analysis setup, again, we got to do the sectioning panel. You can see we are using ammonia this time at 75 degrees. And then in our transient simulation, this is going to run for 5 seconds. Briefly, this cavitation panel, we're going to touch on that in just a minute when we go over DVCM versus DGCM, our 2 different cavitation models. So let's run this model and go straight to the graph results and see what this looks like when we close the valve in only half a second. So you can see how high these pressures reach when we close this valve rapidly. Junction 10, if we go back to the workspace, that is the valve right there. So at this interface, you can see the highest peak in pressure. And then the minimum pressure, if you guys caught it when I briefly looked at the fluid panel, the vapor pressure of ammonia at 75 degrees Fahrenheit is 140.5 psia. Now, if we display this data on this graph, you'll see along this entire pipeline, the minimum pressure reached 140.5 psia, meaning it's cavitating throughout nearly the entire system. Another way you can identify that there is cavitation in your system is we give you a caution on the output tab. So depending on how severe your cavitation is, if your vapor volume is between 0.1 and 10% of the liquid computing volume, then we throw a caution. If it's between 10 and 100%, we throw a warning, and then anything above 100%, we throw a critical warning. So let's go back to the workspace and define our 1 second valve closure and see how this and the 2-second valve closure compare to this just half a second valve closure. So if we double click into the valve, you can see I changed that 0.5 to a 1 right here. And then in this scenario, I changed that 1 to a 2. Now I already pre-ran these before this webinar, so I have the output results right here. I'll move this over just a bit. You can see the differences between the 0.5 valve closure right up here down to the 1 second. The pressure spike is decreasing down all the way to the 2 second where it decreases really drastically. And then on the minimum pressure side of things, when you close the valve in 2 seconds instead of a half a second or even 1 second, it doesn't cavitate at all throughout the system. It never reaches that 140.5 psi pressure. Now, I mentioned that I would briefly touch on our 2 different cavitation models, DVCM and DGCM. So cavitation in and of itself is a topic that we have multiple webinars on, and you can go into crazy detail with it. To keep it simple, the discrete vapor cavity model, or DVCM, is our default model. This is going to be the simplest model and the quickest running, which is why we leave it as our default. DGCM is a bit more complex and takes a little bit longer to run, but we give you both options. So when you are experiencing cavitation in your system, we would recommend that you test them both out and compare the results. And if you're seeing agreement between the two, it's likely that there is cavitation in your system and you should look into it. So I ran the 0.5 second valve closure scenario with DVCM and DGCM. And now let's look at the results and see how they compare. So right here, we're looking at the vapor volume percentage when using the 2 different models. You can see there's pretty good agreement right there, maybe right there, maybe right there. They are pretty far apart from each other right here and right here, but overall, you can see pretty good agreement between the 2. And then looking at the maximum minimum pressures, the agreement looks pretty close as well here. So I'm pretty confident there's going to be cavitation in this system after looking at just those 2 graphs. And then if you want to look at a pressure versus time graph, you can see all the peaks and valleys generally line up. I'd say closer to the beginning of the simulation, they line up much closer, and they stray away a little bit as we go down the line. But it's also worth noting that DVCM oftentimes will give you a little bit more noise than DGCM. So that's why the red has a lot more pressure spikes and sporadic behavior than DGCM, which is a little bit more smooth. So as I mentioned just a minute ago, we do have multiple other webinars discussing transient cavitation in AFT Impulse. Both of these can be found on our YouTube channel, Applied Flow Technology. And these will go into much more detail about all the math, the equations, the modeling, everything behind our cavitation models. Pipe sectioning. This is one of the most important things that AFT Impulse does. So in order to analyze pressure waves traveling throughout your system, we need to be able to compute various different parameters at intermediate points within each pipe. So instead of just giving you output at the beginning and the end of a pipe, we have to section it up, and at each one of these interfaces between the different sections, we call these computing stations. And at each one of these computing stations, we're giving you parameters such as pressures, flows, and anything that you would imagine that AFT Impulse would give you. So we have to section up the pipes, and at each one of these computing stations, we give you all of those parameters. So with that said, the more sections you have, the more computing stations you have, the more work the solver has to do, and therefore the longer your model will take to run. And this brings up the idea of sectioning in order to optimize runtime and optimize accuracy. So increasing the number of sections doesn't always make it more accurate. And that's why we need to be able to optimize this to give you the quickest running model that is as accurate as possible. And I want to touch on the highlights down here before we jump into the software and show what I'm talking about. So in order to section the pipes in the most simplest explanation, we use what is called a controlling pipe. So the controlling pipe is the shortest pipe in your model, and it will dictate how long each section has to be for the longer pipes in the model. So let's say you had two pipes, one that was 10 feet and one that was 100 feet. That 10-foot pipe would have one section, and then the 100-foot pipe would have 10 sections. Now let's say you decrease that 10-foot pipe to 5 feet. That 5-foot pipe would have one section, and then the 100-foot pipe would now have 20 sections. So that brings me to this point down here. Try to increase the short pipes in your system. And you might be thinking, well, if I just increase the short pipes or arbitrarily change the lengths of any of my pipes in my system, isn't that going to change my results? And the answer to that is no. Well, it's going to slightly change your results, but it's not going to change it really all that drastically. And we're going to dive into that in just a minute. It's much better to try to optimize your pipe lengths by rounding them to whole integers, round them to common multiples of each other, increase your short length pipes so the long pipes don't have to have thousands and thousands of sections in them. And then another thing down here is combine your pipes. So Impulse only has to section, say, 3 pipes instead of 5 pipes. If you combine 5 into 3, the solver has to do less work. And we're going to go over how this doesn't actually affect your results as much as you might think. So I have 2 different scenarios over here, one with unfavorable pipe lengths and one with favorable pipe lengths. In this unfavorable pipe length scenario, you can see we have lengths like 34, 8, 13, 6.5, not even a full number. All of these are not multiples of each other, and it's going to increase your runtime quite a bit. If you divide 5200, the longest pipe, by the shortest pipe, this pipe 17, which would be the controlling pipe, this pipe would have 800 sections. Now, by increasing this just to 10 feet, you decrease the number of sections in this pipe to 520. Now, another thing I'd like to touch on is obviously all of your pipes aren't going to be even multiples of one another. And that's where it gets into the more complex sectioning algorithms that we do on the background for you. We take into account things like wave speed and time steps, and that allows us to be able to section the model properly when all of the pipe lengths don't evenly divide by one another. So I'm going to run this model and show you guys how long it takes just for demonstrative purposes. I'm not going to run the entire thing because when I was preparing for this, this was taking 3.5 minutes when I was preparing. I wonder if it's because I'm sharing my screen now. It's taking 7 minutes to run this model. So I'm just going to close that out. I have it pre-run over here in this unfavorable pipe length scenario. Now we're going to go to the favorable pipe length scenario and show you how much shorter we can make this runtime. So you can see we rounded lengths to the nearest 10. So this 34 became a 40. The 8 became a 10. That 6.5, we rounded it to 10. And now if I click run in this model, actually just to make sure, I'm going to create a child scenario. just in case me sharing my screen makes this model run a little bit longer. I don't want to have you guys sitting here and waiting. So if I run this model, you can see, oh, it's running really quickly. So no problem. Takes 30 seconds instead of what we were seeing before, which was 7 minutes, just by rounding those pipe lengths to nice whole numbers. So I'm just going to cancel out of this for now because I already have these two scenarios run. Now we're going to go to our graph results. Let me switch to this scenario and then go to our graph results. So comparing the unfavorable pipe lengths to the favorable pipe lengths, you can see the only differences we see are just consistent phase shifts, if you will, because our pipe lengths are slightly different. So on this profile graph, they're going to show up at slightly different places. However, if we were to combine all of these, you can see the pressure spikes and everything are nearly identical. And the pipe lengths were just rounded to nice, even integers. Now looking at the pressure versus time graph over here, you can see there's hardly any difference at all. You can barely even see that red graph behind the blue graph. So I would much prefer to have a model run for 30 seconds as opposed to 7 minutes if it's going to give me nearly the exact same output and results. And that's why sectioning and sectioning optimally is crucial when you're building a model in AFT Impulse. If you want to learn more about our sectioning algorithms, how everything works, we have a webinar specifically on improving your runtime in AFT Impulse, and it goes into sectioning in great detail. This, again, is found on our YouTube channel. Now we're going to close out this webinar with the fifth and final fundamental, showing you guys some visualization features in AFT Impulse. So we're going to be building this model over here at the right, a simple valve shutoff. And then we're going to be analyzing this using color maps with animations and graphs with animations. So here's the model built. These tanks are defined as atmospheric with some elevation, 50 feet. This one is 45 feet. If you right click and hold on these junctions right here, it pops up this quick access menu for various different parameters that you're defining. It's a quick way without having to double click into each one of these junctions. And this goes down to 5 feet. And then we're going to be defining our valve transient, similar to last time with a CV of 1000. And then the transient will be defined as ramping down from 1000 CV to fully closed over the course of 1 second. So let's run this model. And then we're going to start by showing you guys how to build a color map. So if you navigate on the bottom over here to workspace layers, click plus right here and click color map animation. Once you name this, it will show up over here at the right. And if you click on the little gear icon, you will be able to edit all of the settings of this color map. So you can do just a steady color map or an animated color map. And right now we're going to be animating the absolute values of our static pressure in PSIG throughout our pipe, throughout our time simulation. It's worth mentioning this is running for 2 seconds. And then we had that valve closure that was happening over the course of 1 second. So if we turn this color map on, you can see the animation panel come up here. I almost forgot. One of the most important things in order to build an animation in AFT Impulse is to make sure to save all stations to your output file. So when we were talking about sectioning, we were talking about computing stations. By default, Impulse, in order to decrease the size of your output files, will only save the inlet and outlet of your pipes to the output file. However, that creates a pretty choppy animation. So what you have to do is select all of your pipes, change them to all stations, and this is going to save every single station intermediate along the pipes to your output to make your animations nice and smooth. So if we click play right here, let's look at the pressures as they increase as this valve closes. And then once it finally fully closes, then we'll see how these pressures bounce back and forth between the reservoirs and the valve. So this is just one of our visualization features in AFT Impulse that can be pretty useful when trying to analyze your models. The other way that you can visualize using animations is through our graph results tab. So right here, I've built an animation for the pressure versus length, and then the flow rate versus length. So you can see this animation option down here. I am animating using the output results because I saved all stations. There is an option to animate using the solver, meaning it's going to run the model at the same time while it's animating. But you can imagine if your model takes longer than just a few seconds to run, by doing this, the animation is going to be pretty choppy and pretty slow. So I always recommend save all stations and use the output to animate. So if I play this, you can see the graph rising gradually as this valve is closing. And then once it fully closes, you'll see how the waves bounce back and forth throughout the system. Now it's fully closed, and the waves are bouncing back and forth. Now let's look at the flow rate versus length graph, just as another example of animations. You can change what you're reporting on down here. There are many other options for this. For this one, I'm just keeping it simple with flow rates and pressures. So you can see as the valve starts closing, the flow rate goes down and down and down until it reaches zero flow, and then starts oscillating back and forth with a little bit of reverse flow, forward, forward, reverse, and then it bounces back and forth between that valve and reservoir. Same over here as well. So briefly touching on the highlights again, remember to save all stations when you are looking to animate your model. We have two options for animations, one using color maps on the workspace layers feature, and the other using graph animations on our graph results feature. And again, we do have a webinar specifically on visualization in AFT Impulse, and this will go over some of the things I touched on right now and other things in further detail. Now, before you go, I want to highlight some of our helpful resources that we have for your own model building. docs.aft.com is our documentation and help site. This will tell you everything from as simple to what parameters go into defining a pipe, all the way to as complex as how does the background solver in AFT Impulse work with equations and theory and all of that. Also mentioned a number of times in this webinar, as well as previous webinars, are uploaded to YouTube after they are completed. You can see we have over 200 videos posted there at this point. And then if you need to contact us for any reason, our support team is available at support@aft.com, and our sales team you can reach via sales@aft.com. And for both of us, our general phone number is 719-686-1000. and you'll be able to reach our support team or our sales team depending on the ring group that you select. I want to thank you all for attending. If there are any remaining questions from this webinar, or if you have any future webinar topic suggestions, please email them to webinars@aft.com, and we will do our very best to answer them in a timely manner. Thanks again, and I hope you all have a good day.